Hello and welcome to another video on my channel. In this video I'm going to continue our discussion on developing a symbolic functions space and a symbolic math of functions in Java using operator overloading concept. And to recap from the last video, the goal is to, or the approach here is to create an abstract function class that implements the operator overloading, and for each overloading method it returns an abstract function again. And if you recall, we use anonymous classes and method overriding to override the general methods that all functions should implement. So far we implemented just the get value function, which returns the value, okay? And then we can create subclasses of the abstract function, which could be a constant function, identity, sine, cosine, and all these functions. And then we also overrode the toString method to be able to have a string representation of the objects. Now for the constant function, we also implemented the operator overriding for the assignment operator, so that we can have the directly assign a function object, FC or constant function object, to a primitive type. And if you recall, the compiler behind the scenes, when it generates the bytecode, it actually replaces the direct assignment with this simple factory method, the value of method. Okay, now let's head to Eclipse and continue our work. So in the last lecture we created the abstract function and implemented the operator overloading for the math functions, and then we created the FC, the constant function, and we created the identity function. So let's add the string the documentation here, identity function, f of x equals x. Okay, and with this now we are going to continue our development of the functions. For example, let's say we want to add abs of x, for example, abs function, and this abs function extends the function abstract function class, and it complains because we are forced to implement the get value method, and whenever we pass some x value to the abs function, we have to return the absolute value of it. So you can use the direct definition of absolute value, or just use the abs method in the math class. Here I'm using that, okay? And the toString method, let's go and override the toString method, and toString method is just f of x equals abs of x. Okay, something like this. Now we have abs. Let's go and implement for example sine. Again, this one is extending the function class, and here we have to implement the get value. Okay, and then here I use math.sine. okay, whenever we have a sine object of type function. Well, how do we use this? So let's go back to this example, and I'm going to delete these parts. Okay, and the way we do it, let's say we create an x function. So it's like creating f of x equals x. Let's call it f1. Okay, so f1 of x is x, and let's have f2, which is a new sine object, and this basically creates f2 of x equals sine of x. Okay, and then let's say fsum or fadd equals f1 plus f2. Okay, and the compiler understands what's going on, and In order to show that this is indeed correct, let's get the value of f1 dot get value at let's say math dot pi over 2. And this should return pi over 2, okay, 1.57. And then let's get the f2 get value at pi over 2 should be 1, and let's have the f add, or maybe let's just change it to f3. It makes it easier. f3 2.57, right? So this way of creating a symbolic function space works. Create identity, create sign, and basically create f3 of x equals x plus sign of x. Okay? And you can create other functions as well. For example, f4 equals f1 times f2. So pi over 2 times 1 should return pi over 2. Yes, it returns. But then the problem is that every time you want to create a function, you have to use this new keyword. And then the other thing is that what happens, let's say, what if we want to have, to write something like sign of x, where x is a function, it's not a double variable, it's a function, and sign is also a function. So how do we do this? How do we implement this? Instead of, because right now I'm creating a new sign, but instead of that, what I want at the end is something like this function. For example, f5 equals x plus sign of x, and x should be the identity function, which should be this one, and sign of x should be this object, and then sign of x should return a function of basically type sign or something like that. Okay, so how do we do this? So the way I'm going to do it, I'm going to create a utility class called let's say function math or function ut. And in this class, I am going to create some static stuff. For example, public static function, or maybe, yes, public static function x equals new x. Okay, public static function sign. Okay, no. So we create this x because that's our variable, right? We said we are developing a single variable function space, and our variable is called x. So we create this, and then I want to have a public static function, a sign method, which takes a function x, and then what it returns is what it returns basically a sign function, sign object, and maybe let's call this func. I want to have the sign of this func. So the way I'm going to do it, I'm going to create a new basically let's call this function f sign new sign. So I'm going to create a new sign, but by default, so sign, the sign object is a function of x, right? But what I want is, however, what we want here, sign of a function. So I want sign of f of x. Basically, I'm creating a composition, some sort of composition, right? So the way I'm going to do it, basically, maybe let me just put this here. You probably can guess how I'm going to do this. I'm going to override the getValue method in this sign. So I'm going to override it. Source, override implement, and from the sign I'm going to override this sign. Okay, so I'm creating an object of type sign, but I'm going to override this basically this sign object. Okay, so instead of saying that at each point, at point x get super dot get value and the super is sign, I'm going to tell it to get the value of the super, which is the sign, at func dot get value of x. Okay, and then I'm going to return f sign. I hope this makes sense here. So what we're doing, basically what we're saying is that I want to calculate sign of f of x. So when I pass a function and try to get the sign, therefore I override the get value in the sign object with the input value of func.get of x. Okay, so if I go back here, what I'm going to do here, import a static function math. Everything. Okay, so I'm going to import the static, and now this should work. This expression works. See the beauty of it? This is very beautiful. I have a function x plus sign of x, and this sign comes from, this sign is basically returning a function, and x is my variable, which is also a function, which is identity function. Okay, so system.out.println f5 get value at math.py over 257, and if you recall, f3, basically f3, which was x plus sign of x, was the same object. Let's just delete this. Okay, so the first method is to do it like this: create these objects, identity objects, sign of x, and f1 plus f2. Okay, but then the problem is that it's tedious. Instead, we create some static objects in some utility class. So let's write this down. This is a utility class for symbolic functions. And in the utility class, we basically define our variable as a function object, which is identity function, right? So we defined our x as the variable, which is identity function, and then define composition of functions. For example, sine of f of x, cosine of f of x, etc. Okay, for any function objects that we define, for example, abs of f of x, we can write a utility static class and use this technique of overriding the getValue method in the function object that is basically doing the same thing as the method that we're doing. For example, if I want to do the same thing for abs, but abs, instead of acting on a double value, it acts on a function. And the way I'm going to do it is just exactly the same thing, right? But here I have abs. I create a new abs, but override the getValue method. And at each point x, I call the superclass method getValue, but pass basically the function value. So the superclass, which is abs, is evaluated at the value of this function that is passed in. This is basically implementing the abs of f of x. Okay. Now to test this, let's say function f of 6 equals sine of x. Okay, and then system.out.println basically f6.getValue at some point math.py over 2. Now this works. So sine returns function and x is a function object, which is our variable, which is identity 0.84. Okay, and so what if we wanted to do it the old way with the new keyword? How do we do that? We have to exactly do the same thing as we did in this basically in the function utility class. For example, function f7 is new sine of new sine, but we have to basically override the get value method. Okay, so this is basically the general way of going about this. So the idea is that you create a function objects, and then create a utility class, function math or function utils, and create your static function identity function, and declare it as the variable that you're going to use in your symbolic calculations, and then implement the methods to be able to calculate the composition of the function. Okay, so if you want to calculate for example cosine of f of x, you can, what we do is that we use a cosine of x object and override the get value at x, override it. Okay, so cosine extends function, and in the get value we call math.cosine and x. Okay, and we can override the toString method, and in the function utility we do exactly that. In the cosine we call the cosine object, and everything remains the same. Okay, we call the the get value in the super, which is the cosine, right? And then or function, it doesn't matter, we call the super, and then func.getValue. So sine of pi over 2 is 1, so if I directly calculate the basically sine of 1, now this doesn't work because it's expecting a sine of function, but we are giving it 1. So in order to do that, I have to declare a constant function. Okay, now it works. So the constant function becomes useful in these cases because remember, the value of method was only defined for the constant function. Therefore, it cannot replace a function by a double. It cannot do the assignment on the function. It has to be on the constant fc function. Sine of this get value, so sine of basically sine of x get value at 1. So it's the same as sine of x at pi over 2, because then sine of x gets evaluated to 1, and then sine of 1 is evaluated at basically at 1. Okay, now what are the other capabilities that we can add to our function? For example, we can have differentiation, public abstract double get value. Okay, public abstract function, for example diff. You can do this and return a function, or you can something like this. So if I have a function and I take the diff, it basically it should return a new function which is the derivative of the original function. So this is one way of doing it. Or we can have a numeric method for diff, right? So we can have a diff with double x, which means or we can return an object diff. Okay, now both of them make sense, so let's go with this with returning a diff object. Now once this happens, all these functions, all these implementation of the anonymous classes, they all start to complain. Why? Because if we declare these as abstract, then we have to implement it everywhere. For example, in the add method, adding to a double, the differentiation doesn't change, right? So basically, if I want to implement diff, I just return this function, right? So I copy the original one, this func. Okay, if I add a double to a function, so this is my original function, this function, so the get value method we have to add the double value v, but the differentiation doesn't change because diff of func plus some variable v is equal to diff of f of x, right? So basically this function dot diff. And the same thing happens at everywhere for addition. Everywhere for addition, okay. For subtraction, the same thing, the differentiation doesn't change, the derivative is still the same. Diff of fx minus v is equal to diff of x. So the same thing, the only thing that matters here for subtraction is the reverse. When you do reverse, diff of v minus f of x, okay, it becomes minus diff of x, so minus. And you already understand the negation, so it's fine with it. And then these are for double. I think we made a mistake on the double. If we pass a function here, this function diff plus v dot diff, diff of f of x plus v of x is equal to diff of f of x plus diff of v of x in summation, okay? And the same thing here, v of x plus f of x is equal to diff of v of x plus diff of, so we have to do v dot diff plus this func dot diff. And these are still abstract, so right now we are operating on an abstract level. And then subtraction, reverse subtraction, minus diff, subtract from a function, f of x minus v of x, diff of f of x minus diff of f of x, v of x. Okay, so this minus v dot diff of is, and these are functions, but then the subtraction between two functions is already defined. Yeah, actually we should probably test this, whether or not this works. But okay, maybe let's just let's just leave the rest, and then here, and then for the constant, the diff is basically a new fc function with value 0, right? For a constant function we end up with 0. For x identity function, if I implement diff, I end up with a constant function, okay? New fc 1.0. And note that we cannot do return, we cannot do this return 1.0 because the value of method is not defined for function. We only defined it for the constant function. Okay, so we have to return a constant function. In the sine function, the diff of sine is cosine, so new cosine of x, okay? And in the cosine function, diff of cosine is negative sine, so minus sine of x, basically we can just create an object of type sine, f sine new sine, okay, and then we return basically minus f sine. And back to the function, for the negation we also implement the diff. Diff of negation is basically minus this func dot diff, okay? For the ABS, the differentiation depends, basically it's not continuous, so it has a discontinuity. So what happens here, we have to look at the we have to define it in a piecewise, basically in a discontinuous way. And we can use the sinum function to define that. And for now, let's just leave it at now, okay? Now let's go and see if, for example, the negation works here. If I run this, all of this still works because they're not using differentiation. So let's just diff of f of x equals x, for example. System dot out dot print line, and here I wanna f dot diff and get value at some point 1.2. So f1 is basically x, so we should get 1, okay? f2 is sine, so we should get cosine, and cosine of 0 should be 1. Yes, and let's maybe add the sine f2 plus f1. Let's see if this works. f2 plus f1, it's a function, sine of x plus x, and then we take the diff. Okay, so diff of f1, so we can let's write it here. In order to verify f1 dot diff, get value at 1, at 0, plus f2 dot diff, which is a function get value at 0, and both of them should be 1. So identity function x becomes the derivative is 1, a constant function. Sine function becomes cosine. At 0 it's 1. So now let's look at this. For example, we created this using the utility class funcmath, okay? And basically we can do the same thing. So function f7 equals f6 dot diff, or you can write it directly, sine of x dot diff, and then system dot out dot print line, basically f7 get value at some point, let's say 0. This should be interesting. 1. So let's see what happens here. So if we take the sine of x, the derivative, we get dx times d sine of x dx times basically, or yes, this is the chain rule, right? D sine of x dx and d sine of u du, which u is basically the sine of x, okay? So we should end up with 1 times cosine of x times cosine of sine of x. And then at x equals 0, cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, so we end up with 1, which is correct, okay? So this is the way. Let's also go back and try to finish up all these overloadings. So here we implement this, and this one, let's see, subtract reverse minus this dot diff, subtract and subtract reverse. So this is v dot diff minus this dot diff, okay? And then multiply. Multiply is just v times basically this func dot diff times v, and basically this is a diff of v times f of x equals v times diff of f of x, okay? Now remember, this is not correct for the case where v is not a constant number, then we have to apply the chain rule. So for the reverse, it's the same thing. We write v times this func dot diff, okay? But for the multiplication, if v is a function, then we should apply chain rule. I just want to highlight this fact. So chain rule is diff of f of x times g of x is equal to diff of f of x times g of x plus f of x times diff of g of x, okay? So here we have this func dot diff times v is a function, and then this func times v dot diff, okay? And multiplication in reverse, it's the same thing, so we can just copy and paste this. And division, for division, it's also the chain rule. So for the division with a number is just this func dot diff divided by v, because the mathematical rule is that diff of f of x divided by v is just 1 over v times diff of f of x, right? Reverse, However, in the reverse it's not correct. So in the reverse, basically diff of v, which is a number, divided by f of x. This is minus v times diff of f of x divided by f of x squared. Okay, so what we need to do here is have minus v times this func dot diff divided by this func times this func. All right, and for the division by a function, we should apply chain rule. So we cannot use this simple thing. We should apply chain rule, and the chain rule for division is that diff of f of x divided by v of x. It's like the rule for the multiplication, diff of f of x times 1 over v of x. So we have two functions, and this becomes basically this func dot diff times v minus this func times v times diff, okay, divided by v times v. And the reverse division, it basically becomes the reverse of this expression. So in the reverse, what we end up with is this function, or basically we are calculating v over f of x. So it's v dot diff times this minus this function diff times v divided by this func times this func. And negation, we already discussed this. So let's quickly go and test these. Test division or division of two functions. So let's say function f8 equals sine of x divided by cosine of x. And we know that this is equivalent to tangent of x, okay? And then let's calculate basically function f9 equals f8 times diff, okay? And system dot out dot print line f9 times get value. We know that the derivative of tangent should be 1 plus tangent squared of x, okay? So at pi over 4 it should be 2. So let's say math.pi over 4 2, okay? So this kind of symbolic mathematics works great. Now a more advanced version of this symbolic math is in my MathLib GitHub repository. In my MathLib project, in the function package, there is a symbolic package, and we have an interface. So instead of having so this is a bit more complicated, and the idea was that to have an interface called mathfunc. This is where the operator overloading and basic properties of functions are defined. And then we have our abstract function, top level function, which is math function base. And then all of the basic functions are in this basic package, okay? And I got the idea from this GitHub repository for this kind of symbolic calculations. And you can also go and directly look into this GitHub repository. It's a very good repository, and I highly recommend you check it out, okay? And the way it works is that we have a class called fmath, okay, fmath, which is exactly what I discussed. So we create a static objects for the identity x, y, z. So you can have multiple variables, and function sign, which return. So we also define a sign of a function or other functions that return a function, math function. And we use the math function type to create and work with these functions, and all operators are overloaded for math function type. This interface yeah, so this is a more advanced version, works with more than single variables. You can define multiple variables, and it's a very nice tool to have in your toolbox. Thank you very much, and I'll see you in the next video.